All right. I'm going to get started shockingly on time because I realized when I was doing this talk that I picked the 20-minute slot, and I've got probably about 40 minutes worth of material. Never good, since probably that means I actually have 80 minutes of material. So I'm just going to get started, and people that come in a little bit late will miss the introduction, probably won't miss anything. So this is a talk about a module called Chi. Some people call it CHI, some people call it Chi. Really doesn't matter when you type it, but I always call it Chi. And this is a universal caching module for Perl, and I'm going to talk about kind of introducing the module for people that don't know what it is, and then talk about kind of just a grab bag of features in it. Like I said, I have more than enough material for this, so I'm going to try to pick my features wisely. Okay, so Chi didn't stand for anything. It just kind of sounded like caching. But then people kept asking what it stood for, so I decided it stood for Cache Handling Interface, or someone came up with that on the mailing list. And the basic idea is to provide a standard interface and implementation for Perl caching. This is kind of overstatement of the year when I say this, but it's like a DBI for caching. So I don't mean that this is anywhere nearly as good or important or anything as DBI. I just mean that that's the closest relationship I can possibly think of. The way that DBI abstracts out all of your drivers and gives you a set of common features for database access, Chi abstracts out all of these different drivers where you can store your caches and gives you a nice standard interface and implementation. And when I talk about caching, is there anyone here that doesn't know what caching is? You can raise your hand. Okay, good. But basically, when I talk about, so people think of lots of different things. We talk about caching, there's browser caching, server caching. But when I talk about caching, I just basically mean getting and setting key value pairs with expiration. So the keys can be anything. They can be, deep data structures or scalars. The values can be anything, deep data structures or scalars. And then there's this extra expiration so that if you put it in there and it expires, when you go and get it, it might not come back out. That's basically it. So I did like a search for cache on CPAN, and I got back 193 results. And so Chi isn't even one of them, because Chi isn't even named cache. That namespace was just way too taken by the time I got to Chi. So you might ask why. First of all, how's anyone going to ever find this? I don't know. Branding. It's all branding. It's hard to go against the grain. I wanted to call. There's already even a distribution called just cache. So it was all taken. And I had to go with something different. So, but this begs the question: why do we even need something else? There's already 193 great modules. Tim Tody is great and all, but really, come on, John, did you really need to invent something else? But all these caching modules kind of implement one particular kind of caching and one particular set of features. And cache mem cache d does one thing, and cache fast mem map has some other features, and so on. So I wanted to have a standard set of features in a single place. There's actually I didn't realize when I got into this. I actually just wanted to make it easy to switch between different drivers. But once I got into this, I started realizing how many standard features there are for caching that you don't want to have to implement in every single driver that you implement. So a sense of namespaces, how to serialize keys and values, how to do multi-level caches like L1, L2 caches. Probabilistic expiration is something that I just love because of the way it sounds. It makes me sound smarter than I am. Max size and discard, so having a certain size for your cache and then choosing how to discard items. Logging and statistics collection, so to see how your different caches are doing and whether you should stop caching altogether because it's more trouble than it's worth. And then like whether to compress values, centralized configuration, all these things. It's silly to implement all of these in all of these separate cache modules. It made sense to put them in one place. And then kind of a corollary to that is I wanted to make it easy for new backends to be created. So if you want to cache, in a new kind of storage that hasn't been cached in yet, you should be able to do that with an absolute minimum of writing. And at the time that I wrote this, the default was cache, and it made it kind of hard to create new backends. You had to write a couple different classes, and then you had to define quite a lot. And that was what initially got me into this, was I was sick of that, and I really wanted to make it incredibly easy to write a new driver. And there's also, when I got into this, I was thinking of caching in terms of web frameworks. That's kind of where I come from the Mason world. But I was surprised at how many places you need caches. Once I had a caching framework, I was surprised at the number of places where suddenly I needed a cache. So web frameworks like Catalyst and Dancer, obviously you want to cache a page, you want to cache part of a page. Sessions. A session is basically a cache, right? There really ought not to be all these. A session is basically like the cookie or whatever you get your session ID from is the key, and then you just need some cache. And it has some expiration, like maybe you only want the sessions to last for an hour. So really a session is just a cache. ORMs, like DBX class, rows DB object, obviously can use this. When you want to fetch rows again and again from the database, you might want to cache them so you don't have to keep fetching them from the database. Templating, both Template Toolkit and Mason have some version of caching going on so that if you're going to render the same template again, you shouldn't have to do the work. And then I started getting into even more and more obscure areas. Like I'm writing a code processing module, which I'll be giving a small talk on later on in the lightning talks, that kind of does Perl tidy and Perl critic and a bunch of other things over a whole code base. And I realized you don't want to have to process every file every time. You want to have a cache so that if the file hasn't changed, you don't process it again. So even there, you need a cache. And at some point, I would love to try to tackle Moose startup time and see if there's like a way to use caching there to improve startup time. So the point is, there's lots of places that need caches. Okay, so this is the basic using Chi. The first line is, this pointer I think is laughable, but the first line is you just create a new object, and you really have to pass it two things. You have to pass it a driver, which tells it, are you caching in memory, in a file system, in the database, in memcached, what are you doing? Where are you storing it? And then this will basically map to a subclass or a plugin. And then you need a namespace of some kind. If you don't put in a namespace, it'll default to main. But I'll talk about in the next slide, a namespace is a way of sort of dividing up your caches in your program so that they don't interfere with each other. And then there's kind of two basic APIs for getting and setting things out of the cache. This is kind of the classic way. This is the one that Cache had. This is the one that probably 99% of the cache modules out there have. And in fact, it's kind of, when people expect to get a standard cache object, this is the one they expect. You have a get and a set. So you get some key. If it returns undef, that means it wasn't in the cache. If it returns an object, then it was in the cache. So if it wasn't in the cache, you call some function like, okay, get customer from database with a name. Now you have this object. Now you have to put it in the cache so that next time you won't have to compute it again. So you do a cache set, and this time you give it the same key again. You give it the object, and then you give it some idea of expiration. So this is like 10 minutes, meaning that after 10 minutes, the thing will expire, and you'll have to get it again. There's a lot of other options and so on, but this is kind of the basic thing, and this is the way that cache worked, and a lot of other cache modules work, cache memcached, and so on. There's actually a better way to do this, and Chi is one of the few modules that implements it, I think, although it might have been adopted elsewhere. And these two codes are exactly equivalent, by the way. So in this one, we say cache compute, and we give it the key, and we give it the expiration time, and then we give it a code routine to call if the cache is not there. So it's doing the same thing. It's saying, look, I don't care how you get customer object. If you need to go to the cache, if you get it from the cache, great. If you can't get it from the cache, then run this code to get it, and then put it in the cache. But either way, just hand me back the customer object. Now, can anyone think of why this might be better, using this second method as opposed to the first method?
You don't have to rewrite that as a default.
You mean, right, it's less code. Less boilerplate, right. So that's true. And you also you don't have to put the key in twice, and you might get the key different here, right? Is there any other reason that someone could think?
It's one call instead of two.
One call instead of two calls, right. That's true. Well, underneath, though, to be honest, it's doing a get and a set, so it's probably not really more efficient.
But there's less queuing delay if it's distributed. By having one call.
Maybe that's true, yeah.
You can also change it later more easily if you want to change between returning on depth and getting
Right.
it at the time.
That's true. Okay. And it's a lot easier to read. Okay. I'm going to just kind of put this in the back of your mind. Later on, I'm going to get to some interesting other advantages of this compute, but I'll kind of leave that to you guys. Okay, so like I said, a namespace, this comes from cache, and it was a great idea. A namespace is a way to separate cache keys into silos, where the silos are completely independent. So when you pass your cache a namespace, you can feel confident that no matter what stupid keys you pick, even if you use the key 1 and 0, foo and bar, whatever, it will not interfere with any other namespaces, right? So you can think of it kind of as the namespace being appended to the key. So you take a namespace and a key, and you combine those, and that's what's ultimately going into your cache. That is actually how it's implemented in some of the drivers. So the memcached driver, memcached, is it memcached or memcached? Am I pronouncing it right? Memcached, okay. I don't talk very memcached doesn't have a concept of namespaces, so you have to append the namespace to the key and then just send memcached a key. But other drivers have smart ways of implementing namespaces. But in general, you can inspect and configure and clear these namespaces independently. So for example, you can say, all right, this particular namespace, I want to see what all the keys are in this namespace without seeing any of the others. Or I want to configure this namespace to go to the file system, but this namespace to go to memcached. Or I want to clear everything in this namespace without touching anything else. Now this is not always possible. Like memcached in particular makes this kind of difficult, but in most drivers this is possible. And it's typically the package or the template name that you're in, or maybe the script name. So for example, that just keeps it easy. So every time you're in every time you're in some package and you want to cache, you just give it __ package. You just give it the class name. And then that way you know that your cache is scoped to that package, and no one else is going to touch your cache, and no one else is going to be able to read from it. And if anyone else wants to read from your cache, they're going to have to call a method on you, to read it. So that's a nice kind of scoping going on there. So this is just kind of a survey of the drivers that are out there. This is not complete, but these are kind of the ones that I thought of. There's memory and raw memory. The difference between these being that raw memory, like every other driver, will actually make a copy of your data before it puts it in the cache, and it'll make a copy when it comes out. Whereas raw memory will actually store raw pointers. Raw memory is actually, obviously faster, but it's also kind of goes against the grain, and it's, if you were to replace some cache with raw memory, it would behave differently, and you'd be able to actually, by changing the objects, you'd be able to change what's in the cache. So it's kind of left as a separate driver. But this is a memory cache. File is another one that comes with Chi, and it's just hierarchical, one file per entry. It's, it's very reliable, but kind of slow. You got fast mmap, which is memory map files. It's faster. Berkeley DB is also faster. These all pretty much work on a single machine. And then you get into these sort of distributed caches that work on multiple machines. So you can cache inside DBI, which seems a little strange, but because you're trying to cache what's in DBI, and why would you put a cache in DBI? But if you're computing something, if you're having to get a bunch of stuff from DBI and then compute it, it might make sense to put it in DBI. And actually, some of these DBI drivers are pretty fast, especially like SQLite. And sometimes that's just the only distributed thing that you have. And then there's all these other distributed kind of memcached, Redis, Tokyo Tyrant. There's drivers for all those. I'll show you really quickly. I wasn't sure whether to show the slide. But basically, this is what's involved in creating a driver. All you need to define for a driver is how to fetch from the driver, how to store something to the driver, how to remove, and how to clear all the keys, and how to get all the keys. So if you just create a little subclass and define these 5 methods, you've created a new driver for whatever kind of storage you wanted.
Sounds like Thai.
It is very similar to Thai. In fact, I kind of looked at the Thai interface when I was writing this to make sure I didn't leave anything out. It's a little bit different, obviously, in some of the things. But yeah, basically you're implementing a hash. And notice that in here, you don't have to worry about expiration. You don't have to worry about key serialization. When you get this key here from fetch and store, you can assume that key's already been transformed. If it was a reference to something, it's been serialized. You can assume that the data's been serialized, so the data is not some big object. It's just some serialized data. All you have to do is literally store blobs with a scalar key. So it really couldn't be simpler. Why do I have Moose on the slide? Because Chi is based on Moose, these are Moose subclasses. Yep. At one point, it was possible to make a Chi driver without using Moose, and then I kind of abandoned that effort. It still might be possible, but I just decided to buy into the Moose Kool-Aid and go with it altogether. So. And I highly encourage you all to do that too. Okay, so I talked about this. This fancy-sounding probabilistic expiration, and it sounds all Star Trek-y. This is good for avoiding something called misstampedes, which is another name that I love, and this is from the memcached community. So a misstampede is when you set a cache to expire in, let's say, 1 hour, or in this example, it's 20 minutes. So you set a cache to expire in 20 minutes, and let's say you've got multiple machines, all kind of getting this cache, everything's fine. All of a sudden, the 20-minute moment arrives, and let's say this thing takes 10 seconds to compute. Well, within that 10 seconds, everyone that goes to the cache sees a miss, and they're all going to try to compute it too. And you end up with this thing where 30 processes are all going to the database, all trying to compute the same thing at the same time. That's called a miss stampede, and it can, cause your server load mysteriously to jump every 20 minutes. Like, what is going on? So this was a way to avoid that. This expires variance, if you give it that. It says, don't expire exactly when I say. Expire in some period. And make a random choice for every process that comes along. Because you don't want all the processes having to talk to each other. If you have to sync up and say, wait, no, I'm computing it. No, actually, that guy said he was going to compute it first. That's just way too much syncing and way too much writing and so on. So this is just using probability. So if I say expires variance 0.25, that means that sometime between 15 and 20 minutes, this will start returning undef when I try to get it. And probabilistically, the probability will increase as you get closer to the end. So at 15 minutes, there's a tiny chance. At 15 minutes and 1 second, there's just an infinitesimal chance that it'll return expire. At 17.5 minutes, there's a 50% chance. And finally, when you get to 20 minutes, there's a 100% chance. So the idea is that at 17.5 minutes later, this guy may return undef and may return the value. So that way, you can use this with the compute API, you can use it with the getSet API. The idea is you can just assume that the thing's expiring, but in reality, each process is receiving different value. What that means is that by generally, only 1 or 2 processes instead of a whole bunch of processes will expire and recompute for everyone. So there's Qi builds in a concept of L1, L2 caches. I'm not sure how many people know what L1, 2 caches are, but that name comes from, I believe it comes from processors. The idea that you have this really fast cache, and then if you miss that cache, then you've got a somewhat slower cache, right? And so you want to hit the L1 cache first, and if it's there, great. And if it's not, well, then I'll go to the L2 cache. But when I come back, I'll put it in the L1 cache so that I can get it for next time. Typically, the L1 cache is faster and smaller than the L2 cache, right? So your stuff that you're really accessing often is in your L1 cache, not as often in the L2 cache. So sessions are a particularly interesting problem, and I was actually at work thinking of how to store sessions because we're actually going from one machine to multiple machines, amazingly enough, on our web server at work, and suddenly we can't store them in the file anymore. And so I was thinking, well, if you put them in memcached, the problem with memcached is if it goes down, whoop, you've lost half of your sessions. And if you put them in MySQL, well, that's kind of slow because you're constantly going to the database. So what was actually recommended on the memcached list at one point was put them in MySQL, but cache them in memcached. So when you're reading the session, hopefully you can get it from memcached. But when you're writing to the session, you go to memcached, you go to the database. And that way it'll all stay up to date, but often you'll be getting it from memcached. This is how you implement that in Qi. What I'm saying is that I'm going to create the cache. DBI is the driver. I'm going to give it some connector to connect to the database, and this will connect on demand to the database as it needs to. But then I'm going to get an L1 cache, and I'm going to say, put a memcached in front of that, and here's my list of servers, and so on. So now, gets are going to go to the memcached first, and then if it misses, it's going to go to MySQL, and then it will write back to the L1 cache, right back into memcached. And then writes will always go to both, and removes will always go to both, and so on. So that way, you're hitting memcached most of the time, assuming you're doing mostly reads. You're hitting the fast memcached. You're only having to go to the database on occasion when you read and then when you write. Yeah?
Can you have more than one layer of that, or is it just the 2 layers?
Yeah, you can have more than one layer. So this L1 cache could have another L1 cache. It turned out to be easier this way to do the API where you have a primary and then an L1 cache. But the L1 cache can have an L1 cache. I've never seen it done. I don't know what's going to happen if you do it. So, but it is possible. Another similar kind of cache composition, putting 2 caches together, is a mirror cache. We use this at my other work all the time. They're always changing their file system. We have this ginormous NFS cache system, believe it or not, and it was really fast because it's a net app. But basically, we keep this gigantic, and every once in a while, the thing just gets completely slow and fragmented, and maybe it's not fragmented, but God knows what happens to NFS file systems. And it's just a disaster, and they have to create a totally new mount and move the cache over. But you don't want to just change the cache route, right? If you change the cache route, boop, now you've got 0% hit rate, right? Everything is a miss until you catch up, and that would actually be totally disastrous. So what we do is we have what's called a mirror cache, where I've got my file driver that going to the old route, and then I have a mirror cache going to the new route. So reads are the same. Reads will just go to the old one, right? But writes will go to both. And so what's happening is, as you go along for an hour, 2 hours, 3 hours, all of your writes are being duplicated. Eventually, you're going to have a mirror. You're going to have a copy of everything that's relevant in the cache is going to be in both places. And then you switch to the new one. And you've got a nice, hot, warm, fresh cache there. You could do this not just with the file driver, but you could go, if you're migrating from the file driver to memcached, you could do exactly the same thing. Another thing I came up with was chi memoize. Memoize is to basically take a function and cache the result of that function based on its arguments. I was looking at this for a long time, and I finally realized this is just a cache. We should be able to apply all the chi goodness to memoize. Memoize is a really, really, really old module, great, useful module, but it just doesn't have kind of some of the modern caching features. So with chi memoize, I can do things like expire. I can keep a max of 10 results in my memoize cache. I can use memcached instead of memory. And then I can examine the cache, and if I examine the cache, it returns to me a chi object that I can do all sorts of wonderful things on and clear it and so on. So I just thought this was a nice update of a very old and very good module. It's 11:20, so I'm supposed to stop, aren't I? Should I go on for 2 minutes?
Yeah, you have a few more minutes.
Okay.
If you could stay closer to the mic, it will help our recording, because I think we're losing the audio sometimes when you step too far away.
Okay.
And we're going to try and switch the things over to the other side of the window.
I'm going to have to do this all again, aren't I?
You don't mind, do you?
All right. This is about, no. Okay. So the mystery of why is compute better that I mentioned earlier, right? So there's this compute. Yes, it is less typing, absolutely. It has two other things that I like about it. One is that it makes possible background recomputation. So the idea is, let's say you're getting really close to the end of this 10 minutes when this thing expires. You're at 9 minutes and 30 seconds. You're at 9 minutes, whatever. You might decide, you know what, I'm going to return this old value, but I'm also going to kick off a background process to compute this value, right? Because if someone's getting it at 9 minutes and 30 seconds, locality-wise, probably someone's going to get it pretty soon again. So this is a way to say, because you've given this code reference, you can easily take this code reference and fork off a process or do something, create a mod Perl cleanup handler, or do something that after you've returned the result to the user, you actually go ahead and compute this in the background. I put a star here saying this is completely theoretical. It hasn't been implemented, but I still like the idea. It's hard to implement because you'd have to specify kind of when do you do this, what's the threshold when you background recompute and stuff. I haven't figured out the API, but I still like it, and it's the other great thing about this is that you can actually measure the compute time. So Chi gives you the ability to measure all kinds of statistics, like how long do gets take, how long do sets take for every namespace, how many keys are in your cache, and all this kind of stuff. But if you're using the get-set API, there's no way to tell how long does the thing actually take to compute. And that's a really, really important value, right? You want to know, is this cache useful? If it only takes 1 millisecond to compute the value you're trying to do, then why cache it? So this allows Chi to compute exactly how long this computation takes. And that lets you measure cache utility. And cache utility basically says, is this cache worth it, right? So in the cache case, you have to take, if you're caching it, you have to take, well, you always have to do a get. And then when you don't hit, when you miss, you have to take the cost of a compute and the cost of a set. And sometimes the cost of a set is, is pretty large, right? And when we're going to NFS, it's actually pretty large. So we have to determine all this. Versus, what if we just compute the damn thing every time? Maybe it's faster. And so this ratio is really important. If this ratio is less than 1, then guess what? You should just get rid of this cache entirely. Because it actually would be faster just to compute it every time than it would be to, let's say, set it half the time because your hit rate is only 50%. I'm always arguing this at work where we have over 200 cache namespaces, and we spend a tremendous amount of NFS time caching. And I always say, we don't need all these caches, but I haven't had the proof yet. So what I'm going down now is changing all of these 200 APIs to use the compute API so that I can then compute this and say, see, half of your caches are useless. I don't know if that's true or not. Oh.
I just had a quick question.
Yeah.
The new interface is more elegant, but it seems like it doesn't facilitate explicit cache invalidation. How do you solve for that?
Oh, well, both of those I did not show you explicitly. Yeah, there is an expire call, so you can call up any cache object and explicitly expire it. And explicit expiration is great. If you can get away with, if you can manage to explicitly expire things, that is much, much better than time-based expiration. It's much more exact. It's just really, really hard. We're facing this too, where trying to figure out what dependencies, like if you change this data, what are all the caches I have to expire, is really, really hard. But no, it lets you do that. It just ends up being really hard. So I just mentioned that Chi will, if you tell it to, if you enable statistics, it'll log all these things, like for every namespace, the number of hits, misses, and sets, the cost of a get, set, and a compute, the average key and value size, and it'll give you this nice log file that it then helps you parse, and pretty soon I'll have a web page as well that's kind of open source to let you view all this stuff. Anyway, thanks for your patience. Sorry for taking up a little extra time.